Hello, everybody. Today we are going to continue to talk about confidence intervals. Last time I introduced a concept of a confidence interval in terms of repeated experiments. If you find a 95% confidence interval, for example, of the mean, from an experiment and then you repeat this experiment multiple times, the true unknown value you are trying to measure will be within your confidence interval 95% of the time. Repeated experiments. Or in other words, if you announce a confidence interval, you are saying the true measured value is within these limits, but there is a 5% chance that I'm wrong. Next topic would be confidence interval for count data. I already introduced standard error of the count, C, which is the square root of this number. But what is the confidence interval of the population mean? Well, exact method here is a bit complicated. So I'm trying to explain it in a sort of a hand wavy way. Just the concept, how this is calculated, without going into any mathematical details. Okay, imagine we have this count 5. So k equals 5 is shown here. The horizontal scale is all possible counts from 0 up to 20 shown here, and this is our actual count. And in both top and bottom panels, I show a Poisson distribution or count distribution for a certain mean. And what we are trying to do here is to, well, it's not a sampling distribution, but we are trying to do the same trick as with the sampling distribution. We are trying to cut off 2.5% on each side, on the left and on the right. This is our count, 5. And I find such a distribution, such a mean, that it cuts off, our 5 cuts off exactly 2.5%. You can do it by simply inversing the equation for the Poisson distribution. There is a formula of this, so you can find such a mean. And on the other hand, we can find such a mean, which is over 11 here, that most of the distribution is here, but our count, our 5, cuts off exactly 2.5% on the left. Now we know that we can cut off 2.5% on the right, 2.5% on the left, and the interval between these two distribution is our 95% confidence interval. A confidence interval is from about 1.6 to 11.7, but you can write it as 5 minus 3 plus 7. In practice, you use an R function called Poisson.test, which is designed to do a Poisson test, but it can be used also for finding confidence intervals. If you provide it with a parameter conf.level equals 0.95, it will find a 95% confidence interval on the count for you. This is an example of both standard error and a 95% confidence interval for various counts. And count is here from 0 to 5, and for much higher counts, 10, 30, 50, and 100. What you can see, especially in the left panel, that error bars, whether it's a standard error or a 95% confidence interval, on small counts are really, really large. For example, if you take 5, if you have a number 5, count 5, due to statistical noise, due to counting noise, the confidence interval on this is very large from, well, as you can see, 2 to about 12. That's what we showed before. It makes the relative error becomes a bit smaller when the number is larger, but for very small numbers, error bars are quite large. Another thing I have to mention is someone asked me before, well, confidence intervals on count data, well, they should be integer because we find integer counts like 5. So why is the error from 1.6 to 11.8? Shouldn't they be exactly integer? Well, no, they shouldn't. Confidence interval is not for the sample count. It's where we expect the true population mean to be in this interval with a certain confidence. And the true mean doesn't have to be an integer number. The Poisson mean could be any real number. If you remember our example with horse kick data for Poisson distribution, that was a distribution with a mean of 0.6. So this mean is not a real number. And the same way the confidence interval we are going to produce on count data, the limits of these intervals are not integer. The next one is a correlation coefficient. Just a quick reminder, correlation coefficient measures the level of relation between two variables x and y, and it's a number between -1 and 1. In this plot, you can see some data, x, y data, and a correlation coefficient of 0.82. But if you want to publish this, it's not enough to say that correlation is 0.8 and therefore our samples are correlated, because there is an uncertainty. So if you want to publish this, you have to either provide confidence limits on R or significance of correlation, or even better, both. Well, how do we find confidence intervals on correlation coefficient? A very similar way as we did for the mean. We do a Gedanken experiment, a thought experiment, which is a simulation where we consider a population, a large population of pairs of numbers. And we assume for this simulation that the population correlation coefficient is 0.7. Now we do the same as we did with the mean. We draw a lot of samples of pairs of size n, and these are examples, the first 9 of these draws. And every time we draw a sample of these pairs, we can find a correlation coefficient, but every time, obviously, it's different. So we can build a distribution of the correlation coefficient. This is the sampling distribution. You see immediately that this distribution is asymmetric. This is what we want to do. We want to cut off, again, 2.5% on each side, but that's a shorter bit, that's a longer bit, just because of the shape of the distribution. But if we have, let's say, 100,000 samples, it's very easy just to count 2,500 on each side. And then we will be left with a desired fraction of 95%. That's the interval containing 95%, the central 95% of our samples. We don't know the analytical form of this distribution, so we cannot cut off probabilities here. However, there is a very convenient transformation. It's called Fisher's transformation, which looks like this. You take a natural logarithm of 1 plus correlation coefficient divided by 1 minus r, half of this, you get a new variable, a transformed variable z. And we can build a sampling distribution of z. We did exactly the same when we calculated the sampling distribution and confidence interval for the mean. We took the unknown distribution, we transformed it to something else, which is known, and then we did our calculations. Now we obtain a distribution which can be shown. It's a normal distribution, so we can do all the calculations here. The mean of this distribution is our transformed variable z, and the standard deviation is 1 over square root of n minus 3. This is what Fisher shown. And having these numbers, we can now calculate 2.5% cutoff on left and right, and then come back to our original numbers. Let's do an example. We want to find 95% confidence limits on the correlation coefficient. Our sample contains 30 pairs, and a correlation coefficient R found from this is 0.7. First, we need to find Z. Now you take R, you put in this formula, and you find Z, 0.867. Sigma, according to this formula, is 0.192. And that is the mean and the standard deviation of a normal distribution shown in this figure. So 95% confidence interval corresponds to Z plus minus 1.96 sigma. You remember this number, 1.96, it cuts off the central 95% of the normal distribution. So we take this Z, add and subtract 1.96 sigma, and these are our confidence intervals on Z. Now we reverse this equation and solve it for R. And this is very simple algebra. You can do this and plug in Z lower and Z upper, and you find lower and upper limit on R. And it's shown in these figures. Distribution of Z is symmetric, it's normal. So this is lower and upper Z. Distribution of R is not symmetric, and the error on R is also asymmetric. So you have to write it like this. The error, the 95% confidence interval on R is plus 0.15 minus 0.25. You can do it in R. I just repeated all the steps I showed you a moment ago, but in R, we start with your numbers R and N. We calculate Z, we calculate sigma, then we find this is the number 1.96. We just find it from the normal distribution to have an exact value. And then find limits on Z, which are 0.49 and 1.24, and limits on R. You can do it obviously in a simpler way. You can use a correlation test in R. So instead of giving R and N, you have to provide entire sample. What I'm doing here, you can repeat these calculations in your computer, in your RStudio. I set a seed for a random number. That makes the result reproducible, because what I'm doing is producing X, which are numbers from 1 to 30, is just a sequence 1, 2, 3, up to 30, and Y, which is X plus a random normal variable with mean of 0 and sigma of 7. And because I set seed, random seed to a given number, if you repeat this calculation, you will get exactly the same result as I do. And then you perform a correlation test on your data. So in real life, your XY would be real data, your real measurements. You perform correlation test and you get 95% confidence intervals here. So it's actually very simple. It's just one line in R to find a confidence interval on the correlation coefficient. This confidence interval on R changes quite a lot with the sample size. These two figures show data where correlation coefficient is exactly the same. It's 0.7. However, on the left, there are 6 points, and on the right, there are 30 points. The sample size is 6 and 30. And the confidence interval on the correlation coefficient here is this one, from minus 0.26 to plus 0.96. Is huge. And it also includes 0. That means no correlation at all is within our confidence interval. If you do a test, a statistical test, I will show you later in later lectures how to do this. The p-value is here 0.12. So there is correlation 0.7, but it's insignificant. It doesn't matter. You can't claim that these two data sets are correlated. However, if you perform a similar experiment for n of 30, your sample size of 30, correlation coefficient here is exactly the same, but confidence intervals are much tighter and p-value is small, telling you that our correlation coefficient is much more precise, it's different than 0, and it's statistically significant. Next one is confidence interval of a proportion. Proportion comes up in biological experiments quite often. If you have your mice and treat them with something and then see the effect of treatment, some of them might respond, some of them might not respond to the treatment, and you have a proportion, let's say 30% of mice respond to a treatment. So this is a proportion, is the number of successes divided by the sample size. And success in this case is, well, any result that you consider important. Sample proportion, and I would denote it with P with a little hat, just to distinguish it from the population proportion P. Sample proportion is an estimator of the unknown population proportion. You can imagine this as having an urn with a very large number of white and black bowls. And then you take a sample of, let's say, 12 bowls, and 4 of them are black. So the proportion, our estimator from a sample, this is our sample, is 4 divided by 12, which is 0.33, while the true unknown population proportion is the total number of black balls divided by the total number of balls in this large urn. We are going to build a sampling distribution of a proportion in another Gedanken experiment. So for this, let us consider a population of mice where exactly 13% of them are immune to a certain disease. Then we draw a random sample of size n and find the proportion of immune mice in that sample by doing our experiment. This is our estimator, p hat. And then we repeat this 100,000 times and plot the distribution of p hat, the distribution of our estimator. You see the results on the right for different sample size. This is sample size of 10, 50, and 998. What kind of distribution is it? The hint is here that every time you select a mouse from the population, it can be either immune or not, with a probability p or 1 minus p. So this is a probability of success, failure, and of course, this is the binomial distribution. So if you find that your mouse is immune, you call it a success, and the probability of success is p. This is the 13% in our population. If mouse is not immune, it's a failure, probability 1 minus p. That means that our sampling distribution is actually known, and we can do calculations. If you remember from the first lecture introduction about probability distributions, I introduced binomial distribution, and I showed you these formulas. I don't expect you to remember them, but that's a quick reminder. The mean of the binomial distribution is n times p, and the standard deviation is given by this formula. However, what we have here, if you look at this horizontal axis, this is not exactly the binomial distribution. It's a transformed binomial distribution because this is not the number of successes, it's the proportion of successes. So we don't have a binomial random variable, which I can call x. We have a new variable, which is simply x divided by n. It's a scaled binomial random variable. So when you scale random variable, we also scale its mean and standard deviation in the same way. Because we divide, this is the definition of a proportion, number of successes divided by the total number, n. Which means that the mean of the new distribution is p, because we divide it by n, and the standard deviation of a new distribution is given by this formula, square root of p times 1 minus p divided by n. And this actually is the standard error of a proportion. It is this sigma r is shown here. Is of course it's much larger when the sample size is small, and it's very small when the sample size is very large. If you remember from previous lectures, we found the standard error from the sample, which represents the uncertainty on the mean. And we do exactly the same here. We are finding the standard error of the sample, which represents the width or standard deviation of the sampling distribution. That means that this estimates the uncertainty of the proportion. Because this is standard error, 95% confidence interval would be approximately 1.96 times this, or 2 times this. It works all right for when proportion is not very small or not very large, and when number are large-ish. For example, in this particular case, our estimate given by this formula, it's a very good estimate of a standard error. And if you multiply it by 1.96, you will get a very good estimate of a confidence interval. But when your numbers are very small, you can see this distribution is asymmetric. So presumably upper error would be larger and this error would be smaller. There is a way of doing this by doing rather complex calculations. You can use prop test in R. This is a proportion test. So this is a test of a proportion of 1 success among 10 trials. So our proportion is 0.1. And the confidence intervals on this proportion are like this. They start at, well, almost zero and will go up to 46%. So if you have 1 out of 10, the uncertainty, the 95% confidence interval on this number is very, very large. So you can't simply say that, oh, we have 1 out of 10, so 10% of mice are immune. You have to quote this confidence interval. Let's find confidence intervals of a proportion in a survival experiment. You have 10 mice, you infect them with something nasty, you apply a treatment, and then simply count survival proportion over time. And you can get this result. You start with 1, which is 100%, and then as mice die in the course of the experiment, you have fewer and fewer mice left. But these are just proportions. We need errors of a proportion. Now, if we use the R program I showed you a moment ago, how to calculate the proper confidence intervals on a proportion, this is what you are going to get. And the shaded areas represent 95% confidence intervals for 2 sample sizes, depending whether you have initially 10 or 100 mice. As you can see, arrow bars, the light shaded bars for the small sample size are quite large. It looks much better for the larger sample size, but that might be hard to obtain in real experiments. So when your sample is small, you have to remember that uncertainties of your proportion are quite substantial. The interesting thing happens here. After day 15, we have 0 mice left, but there is still a significant uncertainty in this. So, all the mice are dead, but you have some sort of a zombie statistical mice around here. You have to beware of small samples. And imagine a small number of 10. If you consider count of 10, then the 95% confidence interval on this count would be from 4.8 to 18.4. And the half of this arrow, let's say lower or upper arrow bar, if they were symmetric, is about 68% of the original count. You could say that the fractional error on count is 68%. If you do the same for correlation, you get fractional error of 51%. And on proportion, well, I assume the number 3 out of 10, then error is even larger, 71%. That means if you have a count of 10, and whether you calculate count, correlation, or proportion, your errors are going to be very, very large, of order of 50, 60, 70%. If you want to do something with counts, I suggest strongly to design your experiment that you have at least 30 counts, a sample of size 30, then these errors are much more manageable. I'm going to mention a technique called bootstrapping. This is something which requires a lot of computational power because we are doing lots of simulations in the computer, which nowadays is perhaps not that difficult to do because modern computers have much more power than it used to be 20, 30 years ago. It's a very versatile technique when it can be used when the distribution of the estimator is complicated or unknown. So you want to find confidence intervals on something really weird. Bootstrapping is a really big topic. There are books written on this, but I'll show you one particular example, how to use bootstrapping to find confidence interval of the mean. We are going to use random resampling with replacement. This is what it is. This is our original sample. We have 12 measurements, and we are trying to find the mean and confidence interval on this mean. Obviously, you can use formulas I showed you last time, and I will show you this result in a second, but we can use this alternative approach. And from this, we can find the mean is 18.6. Now we do this resampling with replacement. That means that we randomly pick numbers from this sample. So the first one is 27.7 is this number, then 18.2 is the second number, then 18.2 again, the second number again. So every time we draw exactly one number from the sample, but with replacement. So we can draw the same number multiple times. if you imagine drawing balls from an urn, that would correspond to putting the ball again, mixing them and drawing another ball with a number on it. And from this resampled sample, we calculate the mean, and this time is a different. What we do here, we are trying to randomize things within the sample and force to sort of reveal its internal variability, regardless of the distribution, standard deviation, standard error, and anything else. And you repeat it multiple times, for example, 10, 100,000 times, collect all the means and build the distribution of the mean. This is what it looks like. So first of all, this is not a sampling distribution. It looks like a sampling distribution of the mean, but it isn't. It only approximates it. Just to remind you, sampling distribution of the mean is built from the population. We draw samples from the big population. This is samples drawn from the same sample. We have just one sample of 12 numbers. We just do some sort of reshuffling. And once we have this distribution, this is just a set of numbers. And we can calculate cutoff. We can simply cut off 2.5% of all samples here, 2.5% there. And this is the 95% confidence interval from Bootstrap. And if you do a standard t distribution calculation, this is the confidence interval from t distribution. They are not identical, but they are quite similar. I do not suggest to you to use bootstrapping to find the confidence interval of the mean. There are simpler ways of doing this, but you might encounter something complicated which requires lots of calculations and something the distribution is unknown, and then you can use bootstrapping. This is just an example. Confidence intervals can be calculated in R using functions which are designed for statistical tests, because statistical tests are very closely linked to confidence intervals. And this is a table summarizing all these things. If you want to find a confidence interval of this quantity, mean, median, count, correlation, proportion, you have to use this test. And one last thing, if you want to find a confidence interval on the proportion, 12 out of 87, you can do this, and it's here. It's hidden in lots of these numbers. But if you want to use these confidence intervals later in some calculations, we have to somehow extract them from this. And this is how you can do it in R. So you do your proportion test and store the result in a variable P. This P will be an object in R, and this object will contain lots of information. And one of the information stored in this object is a field called conf.. So you can P and $sign extracts one field from the complex object. And then confidence interval, CI, will be this confidence conf.int extracted from the object. And this CI is actually a vector of two elements, lower and upper confidence interval limit, and you can write it down as CI of 1 and CI of 2. That's everything for today. Thank you very much.